Okay, good morning, everybody. For me, it's a great pleasure, great pleasure to introduce Maral. Of course, she was a student of mine years ago, and it's a pleasure to see how far out she came since the early days when we had to communicate in Persian. This is, of course, a joke. So she's going to talk about a purely algebraic study on Beer X.
Is it working now? Okay. Thank you very much, Aaron. And thanks, organizers, for the invitation. It's my pleasure to talk in ALGA. And the title of my talk is about birational map. Actually, this is a purely algebraic study on birational map. Birational maps from the projective variety x to x. So the question actually is geometric, but our methods are purely algebraic. This is based on a joint work with Hamid Hassanzadeh. Actually, we are still working on this topic. It is a bit new for us. And the first draft of this work is now published in arXiv, but it is a work in progress. Actually, we are happy to say that we dedicate this work to Professor Aaron Simmons in the occasion of his 80th birthday. And we, welcome. And we submitted the first draft exactly in your date of birth. Okay. According to the lecture of Aaron, and with respect to your talk, this lecture will be very simple. I have tried to prepare a few slides with lots of examples. The simplest possible example that I can make it here to have all attendees, and I hope anybody can follow the talk. Thank you. So let me start from the structure, actually, the algebraic structure, and let us start from the Karmana group of Pn. So suppose that we have a rational map. So suppose that we have a rational map from Pn to Pm. So we are talking in a general way. So it can be given by polynomials, homogeneous polynomials of the same degree, f0 and up to fm, all of them in terms of x0 to xm. And we denote it sometimes in the sense that if you consider the coordinate ring of Pn, so all of these polynomials, homogeneous polynomials, are coming from this coordinate ring of degree d. They are all forms of degree d. Okay, and we suppose that there is no non-trivial common factor between them. So the GCD is 1. So we define the polynomial degree of a rational map is d. It means that all of these forms are of degree d without GCD. Okay. So if you consider all monomials of degree d in the polynomial rings with n plus 1 variables, so this number would be n plus d choose d. So if we consider lexicographic order, we can say that any form of degree d actually can be characterized by its coefficient by these monomials. So if you have this coefficient here, we can do a correspondence between a form and between a point in the affine space an, such that in the same direction we have all these coefficients at the coordinates of this point in an, and we can come back. And for any point in an, we will have a form of degree d. Just consider these points as the coefficients of these monomials. So if we have a rational map, so it is given by n plus 1 forms of degree d. So we can do the same correspondence such that, of course, here we are not interested to the 0 points here because these forms are coming from a rational map and all of them are not 0. And we consider all of these coefficients with keeping their order in the same place, in the same affine space, this time of dimension n plus 1 multiple n. But if we have a rational map of polynomial degree, if there is no GCD, so we can say that, okay, another representative for the same map can be given of the same degree d, but by a multiple of a scalar. So they are in the same class. And we would like to do this correspondence also here with the same class, that these 2 points being in the same class by a scalar multiplication. So naturally, we are in Pn. We are in the projective space, actually. So you can suppose that we have the same point in Pn plus 1n minus 1. So any rational map of degree d can be given by a point in this space. So if we forget the GCD, we can say that even we can come back and give a rational map of polynomial degree at most d. So one example, standard quadratic transformation. Suppose that we have a rational map given by these monomials. So what would be the corresponding point of this map? This would be this point in P17. How we can define it? Consider the first polynomial, yz. Actually, it would be corresponding to the first 6 up here in this space. The second one would be corresponding to the second 6 up here, and the third one, yeah. Just we consider these monomials, x2, xy, xz, y2, yz, and z2. So, and we just put the coefficients here. So we have this corresponding point. So we say that sigma actually is a birational map, and we denoted this map is in P2, and because it is given by forms of degree 2, we put 2 here. So it means that sigma is a birational map from P2 to P2 of degree 2. But naturally, you can suppose that all of these birational maps over P2 of degree 2 are naturally seated, are naturally living in the P17. So the question is that, is there any algebraic structure for these corresponding points in P17? Is there any algebraic structure? So it has been answered by Cerveau and Julie Deserti. Actually, in their book was published in archive at least in 2008, but I am putting here the date of the publication. Okay. So they have shown that, yeah, if you consider all birational maps from P2 to P2 of degree 2, polynomial degree 2, living in P17, it is a quasi-projective variety. And also, they have answered the same question, this time for all birational maps from P2 to P2 given by polynomial degree 3. And this also is living in this projective space, and this is also a quasi-projective variety. So among all other things that they have shown also, because we have now an algebraic structure, so you can ask about the property of this variety. And they have shown other properties also. For example, they have shown that P2 actually is an irreducible quasi-projective variety. The dimension is 14, and this is unirational. And for this one, P2 they have shown that this is an irreducible, rationally connected quasi-projective variety of dimension 18. But in 2015, BZ, Calabri, Mella, they have considered all birational maps from P2 to P2 of degree D, this time D bigger than or equal to 4. And they have shown that this variety actually is reducible, is not anymore irreducible. And the dimension always is coming from this relation. It is 4D plus 6. And much more. They have shown that any irreducible component of this variety actually is a rational variety. And lots of other things among that. But they didn't tell us about the quasi-projective variety because actually before of that, Blankfurter in 2013 in their article in Annals of Math, they have considered the vast generality. No, reducible, it means that it can be written as an union of the subvarieties, okay, not of the variety.
It's still quasi-projective.
Yeah, it is still quasi-projective because of this work. Actually, they have shown that for any n and for any d that you consider here in the projective space Pn plus 1n minus 1, this set actually has a structure of algebraic variety. It is a quasi-projective variety. So it's not just a plain case, it is for any n and d. So, and a question arises. Suppose that we have birational maps from Pn to Pn. So if we remove Pn and substitute instead of Pn a projective variety x, what would be happen? So actually it was a question of Blanc in 2017, and he asked what kind of algebraic structure one can put on the birational maps in a general case when we have a projective variety. So we get motivated to work on this and investigate how we can generalize these properties. But even in the beginning, we got stuck because we didn't have even definition, because there were two difficulties even for starting this work. The first problem is that what does a birational map over X of polynomial degree D mean? So the polynomial degree D is not well defined in this case. And the other one is that there is no one-by-one correspondence between the rational map defined over a variety and points in this projective space. I can explain again with an example. So suppose that we have this variety, okay? And suppose that we have the standard quadratic transformation. This time this map can be defined over X and is well defined over X. The equations will be in this variety. Okay, so this is a birational map over this variety X. So what would be the polynomial degree of this map here? Apparently, we can say that, okay, it is given by polynomials of degree 2. So is it correct to say that, okay, this map belongs to Bir X2? If we say it, okay, you can suppose that because we are not anymore in P2 and the coordinate ring of X is not a polynomial ring, we have relation here, and this ring is not actually unique factorization domain. We have relation. Here Y2 is XZ, and if we replace in XZ and replace Y2, what happens? We can reduce the common factor, and we get another representative for the same map, which is ZYX. So what do you say? The polynomial degree is 1 or 2. Maybe you can say that, okay, we can define the polynomial degree of rational map, which is defined over a projective variety, to be the minimum possible degree that is among the representative of this rational map. But okay, let's see another example. The same example in the first slide. Okay, so if you consider, again, the standard quadratic transformation, this is also a birational map over this variety. Okay, it is given by this representative, but there is another and only another representative, polynomial representative for this rational map. It is also of degree 2, but it is not the same one. So if we define, okay, this map is in Bir X2, I mean the degree 2, what happens? We will lose the one-by-one correspondence in P17. Okay, if it is in Bir P2, the first representative is corresponding to this point in P17, and the second representative will be corresponding to this point in P17. So for one rational map, we will get 2 points in P17. So we cannot study in this way the structure, as we don't have this one-by-one correspondence. So it was the first difficulty. And let us talk about the second difficulty. So if we come back to the famous example, so suppose that we have the same quadratic transformation and this variety. Okay, this representative is corresponding to this point. But as we are in the coordinate ring of x, y2 minus xz actually is 0. Adding 0, subtracting 0, adding some multiple of 0 doesn't make any change. So it means that this representative actually is the same as this representative for the same map, because this is 0. So if you add a relation of the variety, doesn't make any change. But if you add this relation, you have another representative of the same degree for the same map, but this time is corresponding to this point in P17. What does it mean? So we lose the 1 by 1 corresponding in this sense. So relation makes this difference. So, and now I'm going to explain how we resolve these problems to get a definition. Suppose that we have a rational map from Pn to Pn given by polynomials f0, fn, coming from the coordinate ring of x. And suppose that we have another polynomial representative for the same map, and they are also coming from k of x. Because these two are the same, are representative for the same rational map, so we can consider the 2 by 2 minors of this are 0 in the modulo the relations in the coordinate ring. So it means that it means that they are proportional, or you can consider that for an element which is the proportional of these elements in the fraction field of coordinate ring of x, if you get alpha, so alpha I is still inside R. It's still an ideal in the R. Okay, good. So any other representative actually giving us an element in the fraction field that makes alpha I inside the R. But it is true also in the other direction. If you get any fraction elements in the fraction field, and we have this property that alpha is inside R, this is corresponding to another polynomial representative for the same map. So actually, thanks, Aaron. I have learned it from your paper. Okay, so the set of all polynomial representative of phi actually is this fractional ideal. And this fractional ideal is actually Homa via R, because we are in a domain case. And this would be exactly R if the grade of this ideal in the coordinate ring be at least 2, or such that if we have at least a regular sequence of length 2 inside I. So it means that if you get a representative for a rational map which has at least a regular sequence of length 2, so it is unique polynomial representative, and another one must be of higher degree. So we can define now polynomial degree, but in this sense we say that this is clear polynomial degree D for this rational map if there exists a representative with grade at least 2, and we define D be the degree of this representative. So we define in this way the polynomial degree. If we come back again to the example, okay, so for this map, the standard quadratic transformation, if you consider this ideal in the coordinate ring of this map, of this variety, the grade is 1. But if you consider another representative, this grade is 2. So the right choice would be this representative, and in this sense, we have a notation. We have this notation. We say that BIR XD is the set of all birational maps from X to X of clear degree D. So if we just omit the Pn and just put X, we should be careful about this D. This is a clear polynomial degree. So what we can say is that, okay, so this sigma actually is in BIR X1, and it is not in BIR X2. Is it different? Yes, it is dramatically different, because actually BIR X2 is living in P17. But when we say that this is in BIR X1, this is corresponding to point in P8. So when we omit the P2 and we just replace by X, we can say that the birational maps can be in the really lower dimension. So now the same standard quadratic transformation for this variety of x is living in P8. It's not living anymore in P17. So the dimension will be reduced. Okay. And notation. We consider all birational maps from x to x, but we put a star here because we want to show that this is the union of all birational maps from x to x, that they have clear polynomial degree. So just let me to clarify some facts. Bx star is inside of Bx. We have equality when we have a unique factorization domain. We don't know yet that if it is a necessary condition or no, but it is sufficient. If we get a unique factorization domain, so they are equal. If no, it is just a subset of the Bx. Okay, let's come back to our examples. Another feature which is showing us the different behavior of Bx and B star x. So suppose that we have x1, this is the smooth normal curve, and the other one is a cospital curve. And again, when we consider the standard quadratic transformation, so we know that both of them are birational maps, but the first one has clear polynomial degree, so it means that has a representative of degree 1 of grade at least 2, but the other has no clear polynomial degree. We know that these two varieties actually are birational, but we will see that actually there is no bijection, canonical bijection between the Bx1 star and Bx2 star. And this is another different feature that we can see in the Bx star. Actually, Bx star, the behavior actually the definition, it's really based on the property of the coordinate ring rather than the birational property. So for the case of the birationality, we know that if we have two varieties that they are birational, so the set of birational x over them are isomorphic. But here, we don't have this because they are representing some different behavior inside of their coordinate rings because we need the grade at least 2. Okay, and methods and main theorem. Our methods are totally algebraic, and just let me start from the main theorem. Suppose that K is an algebraically closed field, and we have an irreducible projective variety. So in this sense, for any projective variety of any dimension, of any polynomial, clear polynomial degree D, so this set would be a constructible algebraic set in Pn plus 1s minus 1. So maybe constructible, I mean that this is a finite union of quasi-projective varieties. Not exactly quasi-projective varieties, but it can be written as a finite union of quasi-projective varieties. Maybe in some sense won't be so surprising for geometers. For example, if you consider a general variety, so and we know that this is, in the case that it is NF, so the birational maps from x to x is equal to automorphisms, and automorphisms of x is finite set. So if we say that, okay, a finite set is constructible, it's not so interesting. But maybe the first place that it would be interesting is the case of the Fano varieties. For example, in the lecture of Paulo Monteiro, he gave us an example of Fano varieties with the set of automorphisms of x to x is infinite. So maybe this was a first place that maybe it's interesting. So because of that, we give an example of Fano varieties, but in an algebraic sense. So suppose that we have a variety of G1 to GT. This is a smooth complete intersection, actually, with the degree less than or equal to the dimension of the space. So it is Fano variety. If you consider that we are in P3 or in higher dimension than T3, so in this case, actually, the set of Bx and Bx star are equal. So the equality happens. And exactly, we can say that in this case, BRXD is constructible. So actually, for saying that, we are using, it was actually the conjecture of Nagata, but was proved by Gertendijk, that was saying that for the domain, and let me see, okay. For domain complete intersection, when for primes of height at most 3, if we have unique factorization domain, the localization of ours is a unique factorization domain. So the ring itself is unique factorization domain. And it is exactly in the case, because we have a smooth, it is locally regular. So, methods. For the methods, we have some closeness and some openness lemmas. So the first lemma is that belonging to an ideal is a closed Zariski condition. What does it mean? Suppose that we have this point in the projective space Pn minus 1, and we just correspond to this point the corresponding polynomial of degree d constructed by these monomials. If this polynomial here belongs to the ideal of J, we say that this point is Vj, inside of Vj. So it is a definition. And this set actually is a closed Zariski, Zariski set. And it is even better than we were thinking. It's a really good set. It is generated by just linear forms. So it is a closed linear Zariski set here. And after that, for resolving the second difficulty, that the same representative of the map can be occurred for adding the relations up to the variety, we are using the dis-elimination index. The dis-elimination index actually is coming from this, the number of generators of this variety. So if we consider n minus s being this elimination index, it is showing that how much we need to eliminate to get the right projective space that we get an unique representative, polynomial representative over a variety that this relation doesn't make any change. So if you eliminate in this way, by these linear forms, we get the right answer. For example, if you consider X be a projective space Pn, so the relations are exactly in linear relation here, so elimination index would be 0. It means that in the case of the projective space, we don't need to eliminate anything because there is no relation other than 0. Okay. And some openness lemma that help us. Belonging to the principal class is an open Zariski condition. So what does it mean? It means that here I am denoting by a bold, but A1 bold actually, each of which are in n-up in the projective space. So each of which are defining a polynomial corresponding to this, the coefficients of this polynomial. So if you consider, so A1, just for being more exact, so A1 bold, it is A11 up to A1n in Pn. And each of which can be considered as a coefficient for the homogeneous polynomial of degree d using these monomials, but this one we are using this coefficient. So if you consider these points and the corresponding polynomial corresponding to these points has exactly the codimension equal to the number of generators, we say that this is actually the principal class J. Of course, J cannot be exceed from the dimension of X because we are talking about the codimension. Another lemma is about the regular sequence. We need this lemma actually to say that, okay, for a representative of a rational map, we need the grade at least 2. So this condition also, if we have A1 and A2 here in the projective space, with grade is equal to 2, it is also an open condition, open Zariski condition. So if you choose the representative of the length, regular sequence of lengths at least 2, you are in the open condition. You have lots of choice to do this. And using, actually, this is a bedrock of the proof of the fourth lemma, that having maximal analytic spread is an open Zariski condition. Maximal analytic spread provides dominant rational map. So we needed to detect the dominancy locus of a map. So, and we will see that, okay, this is an open condition. So you have, okay, if randomly you choose a map and you want to see that if it is dominant or not, your chance is really high. Okay, so, but for detecting the maximal analytic spread, okay, we use exactly the definition and Noether normalization property, and we say that, okay, the Noether normalization locus would be an open Zariski set. What does it mean? You can consider this condition is valid for J, this time from diamond of X to n plus 1. And if you have on this condition, it means that these are all algebraically independent and would be corresponding to the generating, which is needed for Noether normalization. And by induction, we go up and showing that even n plus 1 also is an open Zariski locus. Okay, so we have used this lemma and one thing more. In the general case, when we are working with, oh, I forgot that. Just a remark on the dominancy. About the dominancy is that, so one can use the Jacobian criterion to detect the dominancy of a map. It means that you can consider the Jacobian matrix and you consider the rank of the Jacobian matrix. If the rank of the Jacobian matrix is exactly equal to the dimension of the image of the rational map, so we have a dominant map. But the problem is that, first, it is characteristic sensitive, and it is not valid for any characteristic. And another is that the version of the Jacobian criterion has been announced for the polynomial ring. And if we reduce to the coordinate ring by a relation, it is not valid necessarily. In general, it's not valid. For example, if you consider this rational map, it is birational map. It is actually it is a monomial Cremona map. Yeah. And okay, there is a criterion of Aron and Villarreal. They have announced in 2009. Yeah. For saying that if this is really a birational map or not, you just need to consider the exponent matrix. It is actually, their criteria actually is characteristic free. So you can consider the exponent matrix, and if the rank of exponent matrix is equal to the polynomial degree, so it is a birational map. So in this way, this is a birational map here. So it is dominant. But if you consider the Jacobian matrix and consider the rank of Jacobian matrix in characteristic 2, the rank of Jacobian matrix is 2, is not 3. So by Jacobian matrix, you will say that, okay, it is not dominant, but it is a dominant map. Actually, it is a birational map. Another thing that, I don't know if I have time or not, in a conversation with Aron 2 days ago, he mentioned, actually, he recalled it to me again, that, okay, if we are not in the projective space and we just reduce a bit to the variety, what happens for the Jacobian criterion? For example, suppose that we have in this variety, suppose that this is F, and suppose that we have a rational map, which is a polar map of F from P2 to P2. So it is given by forms which are the partial derivatives of F with respect to X, Y, and Z. Obviously, this is a birational map. So if we just restrict it to the variety V of F in P2, so we are going in VF star here. Okay, and this is due to by Segre that the dimension of Vf star is exactly equal to the rank of the Hessian of F modulo the relation of F minus 2, mod of F. Okay, in this case, when we are working with the gradient, with the polar map, so the Jacobian matrix is exactly the Hessian of F. So it is exactly the Jacobian of the gradient of F. So it means that in this case, if you consider the Jacobian of this map, we will see that the rank of this Hessian matrix is 3 even mod of F, and 3 minus 2 is 1. It means that the dimension of MH is 1, but the rank of the Jacobian matrix is 3. It is strictly bigger than 1. And it is a very weird nature of the Jacobian matrix here, because in general, when we are working over the projective variety, always the rank of the, for general project, when we have maps from Pn, let's say, to P, can be EPL. Okay, if you consider the rank of the theta, the rank of the Jacobian, the rank of the Jacobian is always less than or equal to the dimension of the image. I would like to show that this by the dimension of the spatial fiber. If we have characteristic 0, the equality occurs. If we don't have characteristic 0, it is always less than or equal. If we don't have characteristic 0, but if we have that the relations coming from here, f0 up to fm, if they are all algebraically independent and unirational, so again, equality occurs. But in the case of the projective space, we have always less than or equal. But in this, even a simple case, here the rank of Jacobian is strictly bigger than the dimension of the image. So it is another different feature when you change Pn and put a variety. And you can see that even the behavior is in the contrast of the projective space. So let me continue and talk about another result that was helpful to show. In the general case, when we are working in projective space, we know that when we have a rational map, the degree of the inverse is at most d power n minus 1, birational map of Pn. I mean a birational map of Pn of degree d. So the degree of the inverse is d power n minus 1. But when you consider a birational map over a variety x, we didn't have in general the degree. But it was done in 2017 by Hassanzadeh and Simis. They have considered a rational map, actually the birational map, defined over a variety of x. And they have shown that actually there is a bound for the inverse of this rational map with this number. This is a polynomial in terms of the polynomial degree, dimension of the x, and this is the maximal degree of generators of the relations of x. So what we need really, it was a bound. Okay, if we have this bound, we can continue. And in this sense, we start our demonstration, okay, the proof of the main theorem. And now the proof of the main theorem comes back to the fact that let's consider all the class of representative of a rational map over Pn of degree d. Can have GCD? Yes, can. Okay, and the subset of that, we consider all that class of this rational map that are birational over x. So it means that they are well-defined over x. And the equations of this rational map satisfy to the relation of this x. And it is, moreover, it is birational map of degree d. It's not the clear degree, but it means that there exists a representative of degree d. Inside of them, there exists the class of all these rational maps that have clear polynomial degree. So they are living inside them. What happens for Brx? Actually, from h tilde of d to Brx, we will have a surjectivity. So it means that we get an element, we go to the class of this element. So it is just surjective. Okay. Oh, 1 minute. Okay. So we have this corresponding between Pn, and we have this corresponding between two sets. Actually, these sets here, we have a closed set in the demonstration, okay, in the proof, and we have shown that this dominancy locus is an open set. And here we had two open sets, G2 and Nn plus 1, one corresponding to the clear degree, another corresponding to the dominant. And the intersection with this closed set, it's showing that actually HD and H tilde D are quasi-projective variety. But what happens for the BRXT? If you consider these relations coming from the linear relations from the first beginning of V of J, here inside of the relations of X. So we have a surjective map from H tilde of D in BRXT. And we have, if you consider D prime here, be the image, restricted image of D over H tilde of D, we get a morphism here. And this image actually is in a bijection relation with BRXT. So as H tilde of D is a quasi-projective variety, as this map is a linear map, actually is a finite type morphism, we use the Chevalier theorem to show that the image of quasi-projective variety is constructible, so BRX is constructible. So as a corollary, we can say that, okay, if we have a polynomial degree less than the minimum generating degree of Ix, BRXT living here is a quasi-projective variety, and in a specific case, if you just put Pn here instead of X, this is living in this place, this is a quasi-projective variety for any n and for any d. Okay. But some open questions. Okay. BRX star is not a group in general. We know that when we are studying the BRX, we can consider three structure, topological structure coming from the topology which is defined by Demazor-Serre, algebraic structure as an algebraic variety, and group structure as a group of, for example, group of all, group Keromanoff group, or group of all birational transformations. But here in general, it depends on the variety. And open questions is that for which kind of varieties BRX star is a group? For which kind of varieties BRX star is a simple group? And if we have a group, so what would be the sequence of the degree of the composition of this map, polynomial degree? So these are open questions over the structure of group structure, actually, of this set. So thank you for your attention.